now that we've looked at a few elements of a rational function, we want to expand on those. We looked at how we would describe the domain. We looked at what a rational function even was. Now we want to get a little bit more specific. We talked about when we had a rational function, we would have a vertical asymptote and a horizontal asymptote. So the first thing that we want to do is focus on the vertical asymptote. Now, when we look at a vertical asymptote, this is what we're looking at is a place of discontinuity, all right? Now, in a graph, I can have a couple different types of discontinuity. A vertical asymptote is going to be one type of discontinuity, meaning that the graph cannot be continuous because it must jump over that line, that boundary, right? Another type of discontinuity that we have is going to be a hole, or what we call removable discontinuity. So this will literally look like a point, but it's an open circle because it's representing one specific point, one value at which the graph cannot be. Different than a vertical asymptote, which is an entire line where the value cannot be, where the graph cannot be. So both of these things are going to be places of discontinuity. Now, when we looked at the domain of our function is going to tell us where the graph cannot be and where it can be. So when we were looking at our domain of a rational function, we set that denominator not equal to 0, and we said, okay, well, we cannot be, say, the number 3, right? So if we cannot be the number 3, the very next question should follow, well, why can't we be the number 3? Is it a vertical asymptote? Is it an entire line at -3 that we cannot be? Or is it a point at -3 that we cannot be? So that's where we get into vertical asymptotes and holes. So I want to show you what that looks like, just so we can kind of get an idea of what I'm talking about here. So if we look at this function here to the right, so you can see the difference, hopefully, between a vertical asymptote and this hole. So a vertical asymptote is going to be here, this kind of dashed line. So this vertical asymptote is showing us that the graph is going to approach on both sides off to infinity, okay? Meaning that the entire line at 3 will never happen, all right? So x equaling 3 is our vertical asymptote. It is a point of discontinuity, or it's a spot of discontinuity. Now, we also have this removable discontinuity, or a hole, at this -1. So notice here, I'm still going to approach that open dot, but instead of going off to infinity, I'm approaching a number on both sides. So that's going to be the difference here. In our vertical asymptote, we're approaching an infinite amount, whether it's positive infinity or negative infinity, as we get close or as we approach that vertical asymptote. As we approach a removable discontinuity or a hole, we're approaching a single number value, all right? So we can also see the graphical difference. One's a vertical asymptote, dashed vertical line, and one's an open circle as you get to that number. Both of these we would have found when we talked about the domain. So if I were to talk about the domain of this function, what I would say is that the domain would be from -infinity to -1, right? I'm going to have to jump over that -1. I'm going to go all the way until 3. I'm going to jump over I'm going to jump over 3 and then go off to infinity. So in my domain, I found that x cannot be -1 and x cannot be 3. But what we didn't determine in the domain was what type of discontinuity did we see. So when we look at this, it's easy to tell from a graph because I'm either seeing a line or I'm seeing pieces of the graph going to infinity, or I'm seeing an open dot or kind of a hole where I'm approaching on both sides, that exact number. But from an equation, it's a little bit different. So let's look at from an equation how we would determine the difference between a vertical asymptote and a hole. All right, so let's say we have the function f of x equals x plus 2 over x squared plus 7x plus 10. All right, now when we look at this function, right, remember the idea is that we're looking for the domain, because I noticed that the hole and the vertical asymptote are included in that domain. So I'm still going to look at that denominator. However, the domain itself doesn't differentiate between the 2 points of discontinuity, or the types of discontinuity. So it's not enough to just look at the domain anymore. I must also compare the denominator to the numerator. So what I'm going to actually do when I have an equation is I'm going to look at the numerator, x plus 2, and the denominator, right? We need to factor that denominator, which is going to give me x plus 2 and x plus 5, right? Because 5 times 2 is 10, 5 plus 2 is 7, all right? So now that we have factored, what we want to do is we want to look and compare the numerator and the denominator. So as I look at the numerator and the denominator, I notice that they share a factor. They have a common factor. So what I want to do is I want to remove that factor that they share. Well, that sounds familiar. I want to remove removable discontinuity, right? I want to remove x plus 2, which means that x plus 2 cannot be 0, meaning that x cannot be negative 2. I removed it, so that is going to be my removable discontinuity, or what we like to call a hole. All right, so I've removed it from the equation. So now we say, okay, well, after we've removed anything that we can, what's left in the domain for me to look at? So think about, if we were looking at this domain, we've removed that negative 1, right? It's removed now. The only thing left over would be the 3. That's how we got that it's a vertical asymptote. So we're going to do the same thing here. We've removed that x plus 2. Now the only thing left over, remember we care about the denominator because it's the domain. The only thing left over is that x plus 5. Therefore, x cannot equal negative 5. So that's going to be our vertical asymptote. Okay? So that's what I mean here by we're going to take any factors that cancel off, we remove them, set it equal to 0, and solve, right? So our removable discontinuity or hole would be at x equals negative 2 for this function. Then anything after I've removed the hole, if there is a hole, right? Anything that's left over in the denominator, which was our x equal negative 5, would be our vertical asymptote. All right, so let's look at one where we do it all together, kind of without explaining in the middle there. All right, so let's say we have x squared, let's see, plus 10x plus 24 over x squared plus 8x plus 12, all right? So what we want to do here, if I'm looking to determine if I have a vertical asymptote or a hole, or maybe they just ask me for the vertical asymptote. Well, I can't determine what the vertical asymptote is until I've removed any holes. So I'm going to start off by factoring the numerator, all right? So numbers that multiply to 24 and add to 10, that's going to be 6 and 4. Numbers that multiply to 12 and add to 8, that's going to be 2 and 6, right? So now what we want to do, after we factor the numerator and the denominator, I'm going to see if there's anything that I can remove. Well, yes, I can remove that common factor, x plus 6. So x plus 6 gets removed. That means x equal negative 6 is going to be a whole or a removable discontinuity. Then whatever's left in the domain. Now, I do not care at all about this x plus 4. I don't need it anymore because it's in the numerator and it did not become removed. Okay? So all I care about now is the denominator. I see I've got an x plus 2 left, which would give me x equal negative 2 to be that vertical asymptote. I'm just going to abbreviate there. All right? So looking at a vertical asymptote, it's a line of discontinuity. Looking at a whole, it's a point of discontinuity. Both of them are x values, so I'm looking at the domain, which means I need to factor the top and the bottom, remove anything that's in common. What's left over in the denominator would be the vertical asymptote. Now, something to remember in all of this is that I can have multiple vertical asymptotes. So I can have multiple vertical asymptotes and wholes, or I can have none. So sometimes I might end up not getting to cancel anything and I have 3 vertical asymptotes. Sometimes I might cancel everything and all I have are wholes. Maybe I have some that cancel and some that don't. All right, so just remember, it's not always going to be, oh, one of them has to be a vertical asymptote and one of them has to be a whole. It doesn't have to work like that.